Hello and welcome to Data Science for Ecologists in R. In the last video, we learned how the least squares estimates in the linear model are distributed. This is an important prerequisite for today's video, in which we will learn how the least squares estimates can be used to make inferences about the true parameter values. To illustrate the underlying thought process, we will consider a small, practical example. More specifically, we would like to find out how the blood pressure changes in response to the dose of a certain drug. For this purpose, data from 30 subjects is available, which can be visualized in this scatter plot. After some consideration, we might come to the conclusion that the data is best explained in terms of a linear model. This means we assume there is an unknown true linear relationship between the drug dose and the change in blood pressure, and deviations from this trend are independently normally distributed with an unknown true variance. Consequently, we conceptualize our sample as one of the infinitely many possible samples that could result from these assumptions. Remember that this stochastic nature of the data was essential when we derived how the least squares estimates are distributed. Based on the sample we have, we can now calculate the least squares estimates. For beta 0, we get a value of 0.47, and for beta 1, a value of minus 0.42. These parameters define the blue line as the estimated linear function. With this function estimate, we can calculate the estimate for the error variance, which is 3.5. Let's now briefly review how the least squares estimates are distributed by taking beta 1 as an example. The estimate for beta 1 follows a normal distribution with the true parameter as the mean. Furthermore, we learned that the variance of this normal distribution can be calculated by using the true error variance. Unfortunately, the true error variance is not known, but we do know that 3.5 is an estimate for it. For the moment, let's just assume that we can use the estimated error variance instead of the true error variance. If we do that, we obtain 0.04 as the variance of the least squares estimate. As we learned in the last video, the variance does not depend on the true value of beta 1. This means we know the distribution of the estimate no matter what the true parameter is. For example, if the true parameter is minus 0.2, then the estimate would be normally distributed with a mean of minus 0.2 and a variance of 0.04. Likewise, if the true parameter is 0, then the estimate would be normally distributed with a mean of 0 and a variance of 0.04. And the same would of course hold for any other parameter value. Of course, we don't know what the true parameter is, but we can simply assume a specific parameter and compare the resulting distribution with the observed estimate to obtain a so-called p-value. For example, if the true parameter is 0, then we know that this would be the distribution of the estimate. The estimate that we observed is minus 0.42, and just by looking at the plot, we can see that our estimate seems somewhat unlikely given that the true parameter is 0. We can quantify this intuition by calculating the probability to obtain an estimate that is at least as far away from the true parameter as the one we observed. This comprises values less than or equal to minus 0.42 or values bigger than or equal to plus 0.42. The area under the corresponding parts of the curve is 0.036. That means if the true parameter is 0, then the probability to obtain an estimate at least as far away from the true parameter as the one we observed is only 3.6%. This measure is called the p-value and is usually expressed as a decimal number. Since the p-value is quite low, we have evidence against the assumption that the true parameter is 0. It seems much more reasonable that the true parameter is somewhat smaller than 0. For example, if the true parameter is minus 0.2, then the p-value is 0.272. Since this is not a particularly low value, we do not have any evidence against the assumption that the true parameter is minus 0.2. However, this should not lead us to believe that the true parameter really is minus 0.2. In fact, there are infinitely many parameter values under which the estimate we obtained is not that unlikely. A nice way to summarize such parameter values are confidence intervals. The 1 minus alpha confidence interval contains all parameter values for which the observed estimate leads to a p-value bigger than or equal to alpha. In our example, the 95% confidence interval for beta 1 would range from minus 0.813 to minus 0.027. To illustrate how this interval was obtained according to our definition of the confidence interval, let's look at the following animation. It is evident that for parameter values sufficiently close to the observed estimate of minus 0.42, the resulting p-value is bigger than or equal to 0.05. These parameter values are then included in the confidence interval. Alright, let's quickly summarize the ways we can use our estimate for beta 1 to make inferences about the true parameter. First, we can compare the observed estimate with the distribution of the estimate given a specific parameter value. From this, we obtain p-values, which indicate how much evidence there is against this parameter value. The lower the p-value, the more evidence there is. On the other hand, we can determine confidence intervals, which contain all parameter values for which the estimate we observed results in a p-value above a specific threshold. To obtain the p-values, we needed the variance of the estimate. We calculated it by using the estimated error variance. However, in the last video, we learned that it depends on the true error variance. Therefore, the way we calculated the p-values was a little bit imprecise. Using the estimated error variance instead of the true one adds uncertainty that needs to be taken into account. Without going into the details, let me just tell you that this can be done by comparing the observed estimate with a t-distribution instead of a normal distribution like we did. The additional uncertainty leads to slightly larger p-values and wider confidence intervals. However, the differences in the results are already quite small for medium-sized samples, as you can see by looking at the red values. Therefore, for an intuitive understanding, the normal distribution is sufficient. Alright, this concludes our small theory module on linear models. In the next videos, we will learn to use R functionality to fit linear models. And since the validity of the results depends crucially on the correctness of the assumptions, we will also get to know tools to check for this. See you soon!